15, 12, 11, 10, 9, 8, 7, 6. Go for main engine start. Main engine start. 2, 1. Booster ignition and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
Our modern rocket ships allow us to overcome the bonds of gravity and reach unexplored frontiers. Space exploration is symbolic of our culture's enormous interest in scientific progress and deeply permeates our lives. Children dream of becoming astronauts. Scientists contemplate manned missions to Mars. Our 3,000 operational satellites allow us to view detailed maps of the Earth, talk on cell phones, and watch hundreds of TV channels. We value space so much that NASA's 2009 budget is $17.3 billion. But how are we able to escape Earth's atmosphere and journey into the great unknown? The story of space exploration begins in 1642 Lincolnshire, England, where the great physicist Isaac Newton was born. Newton's ideas are the foundation for modern space travel, paving the way for all our expeditions beyond Earth's boundaries. Newton was a troubled child. He spent most of his time tinkering with mechanical objects. Newton built miniature windmills, sundials, and clocks rather than socializing with his peers. At age 12, Newton became interested in the nature of the cosmos. He was especially intrigued by math and the causes of motion. In 1661, Isaac Newton went to Cambridge University. Newton buried himself in his studies, often working on multiple projects until 2 or 3 in the morning. Newton continued to probe his childhood passions for math and science, but he was unsatisfied with current mathematical knowledge. What if x was constantly changing? There was no way to calculate constantly changing values, so Isaac Newton invented one: calculus. Not only did Newton use calculus for much of his later work, it is directly influential for space travel today. Calculus is necessary to figure out a spaceship's non-uniform acceleration, the radii and periods of orbits, and the rotation necessary for space stations to simulate Earth's gravity.
Calculus is the study of motion, and since going into space obviously involves motion at great speeds and great distances, calculus is a very valuable tool in calculating distances, rates of change, rates of speed.
By age 22, Newton had invented an entire branch of mathematics, but no one knew. Newton was terrified of criticism and had no thirst for fame. He said, "I see not what there is desirable in public esteem, were I able to acquire and maintain it. It would perhaps increase my acquaintance, the things which I chiefly study to decline." Newton preferred solitary study to popularity and refused to publish his work. Instead, he returned to the familiar environment of Cambridge, becoming a lecturer in 1667, although few could follow his lectures. Newton's unpopularity with his students gave him more time to work on motion and mechanics. From 1685 to 1687, Newton did little but calculate. The result was the greatest scientific treatise ever written, the Philosophiae Naturalis Principia Mathematica. The Principia included Newton's 3 laws of motion and the law of universal gravitation. These laws are vital to our modern understanding of physics and continue to hold true today in all conditions that do not involve the speed of light, extreme temperatures, or quantum sizes. Newton's book revolutionized science with its principle that all motion follows the same laws, even in space. Newton destroyed Aristotle's view that an object's elemental composition determined how it moved. Motion in space worked just like that on Earth. All motion in the universe could theoretically be predicted with Newton's new ideas, supporting scientific revolutionary René Descartes' view of the universe as an elaborate clockwork machine. Isaac Newton continued the work of scientists like Copernicus and Galileo with his revolutionary book. He said, "If I have seen further, it is only by standing on the shoulders of giants." But though Newton had come up with the fundamental ideas necessary to reach space, he was afraid to publish them for fear of criticism. Luckily for today's astronauts, fellow scientist Edmund Halley convinced Newton to publish the Principia in 1687. Halley wrote of Newton in the book's preface, "Nearer the gods no mortal may approach."
He gave us a system of laws that essentially uses forces to explain how and why things move. And it's a very comprehensive way of looking at things and allows us to do some intricate calculations that, of course, took us to the moon.
Newton's first law states that an object will continue in its state of rest or constant motion unless acted on by an outside net force. This principle is demonstrated by an astronaut in space, far enough from any large bodies that all gravitational forces are negligible. If the astronaut throws a wrench, it will continue in a straight line forever unless it encounters another force. With the first law, scientists are able to understand the fundamental cause of motion and properly operate without gravity. Without an understanding of the first law, an astronaut is helpless when working in space. Newton's second law states that net force equals mass times acceleration. The second law is the basis for nearly all physics calculations. Without it, scientists could not figure out the amount of force needed to accelerate rockets into space, or even build rockets at all. In fact, the very unit of force is called the Newton.
The second law says that you need a net force to accelerate something. So, what sort of things are going to use for net forces? You can use the rocket engine, of course. Also, you can use an object's gravitational pull.
Newton's third law states that forces come in pairs. Each force is balanced by another equal and opposite force. A fly that hits a truck's windshield exerts the same force on the truck as the truck exerts on the fly. But due to the second law and the fly's small mass, the truck's acceleration is unlikely to be noticed by its driver. The third law is the basis for launching rockets. The push on the rocket's exhaust gases creates an equal and opposite force that propels the rocket upward.
Essentially, I think early thoughts were that you needed to push against something for a rocket to take off. And so the question was, how would they operate in a vacuum since there's nothing to push against? And the third law shows that question that answer is rather absurd, in that a rocket could propel itself through space because it's essentially, reacting against its own exhaust.
But the Principia's contribution to space travel does not end with the three laws. Newton also calculated the very force that keeps us bound to Earth. While scientists had long suspected the equation of gravity, they were unable to prove it. The story of Isaac Newton's discovery of the law of universal gravitation is legendary. In 1665, as the bubonic plague ravaged England, Newton moved back to the country to avoid infection. There, as he did much of the ceaseless thinking that led to the Principia, he is said to have seen an apple fall and realized that the moon was held in orbit by the same force that made an apple fall to Earth. After he realized that gravity worked even in space, he designed a thought experiment to demonstrate how to overcome its effects. Newton imagined a cannon on the top of a mountain. A cannonball it fired would travel a certain distance before crashing to Earth. If the cannon were somehow able to fire the ball fast enough, it would be able to travel around the Earth. If fired even faster, it would escape the Earth's gravitational pull completely. Without the exact law of universal gravitation, scientists would not be able to calculate how to make it into orbit and out of the Earth's gravitational pull. Scientists must take the gravity of all large celestial bodies into account to make accurate calculations for the flight path of spaceships. By discovering the nature of the bonds that tie us to Earth, Newton was able to overcome them. Today, Isaac Newton's laws are used by scientists every day. They falter only in theoretical and extreme examples which are of little relevance to space exploration. Even Albert Einstein, who came up with theories of relativity that challenged Newton's laws, acknowledged his impact. Einstein said of his hero Newton, "The concepts that you created are even today still guiding over our thinking in physics." Without Isaac Newton, we would be forever grounded, watching the stars but unable to reach them. Our children would not dream of escaping gravity's grip. They would not even know how gravity held them bound. With Isaac Newton's ideas, we can send satellites around the globe and astronauts far beyond it. From its humble beginnings in Lincolnshire, the space program has made incredible gains, and it is difficult to imagine life without it.
I told Michael you guys are up there, and he said, "Who's driving?" That's a good question. I think Isaac Newton's doing most of the driving right now.